In this video, we're going to digress a little bit and talk about how compilers handle errors, and in particular, what kind of error handling functionality is available in parsers.
A compiler has two relatively distinct jobs. The first is to translate valid programs. That is, if it gets a program from a programmer that is correct, is a valid program, it needs to produce correct code for that program. Now, distinct from that task is the job of giving good feedback for erroneous programs and even just detecting the invalid programs. So we don't want to compile any program that isn't a valid program in the programming language. And programming languages have many different kinds of errors. Here's just a few. So for example, we might have lexical errors using characters that don't even appear in any valid symbol in the language, and these would be detected by the lexical analysis phase. We could have syntax errors, and these would be the parsing errors when all the individual lexical units are correct, but they're assembled in some way that doesn't make sense, and we don't know how to compile it. There could be semantic errors, for example, when types mismatch. Here I've declared x as an integer and used it as a function, and that would be the job of the type checker to catch those. And then, actually, there may be many errors in your program that are not errors of the programming language. The program you wrote is actually a valid program, but it doesn't do what you intended. You actually have a bug in your program. And so while the compiler can detect many kinds of errors, it doesn't detect all of them. And once we get past what the compiler can do, then it's up to testers and users to find the rest of the problems in the programs. So what are the requirements for good error handling? Well, we want the compiler to report errors accurately and clearly so that we can identify what the problem is quickly and fix it. The compiler itself should recover from the error quickly, so when it hits an error, it shouldn't take a long time to make up its mind what to do before proceeding. And finally, we don't want error handling to slow down the compilation of valid code. That is, we shouldn't pay a price for the error handling if we're not really using it. I'm going to talk about three different kinds of error handling. Panic mode and error productions are the two that are used in current compilers. So these are actually things that people use today. Automatic local or global correction is an idea that was pursued extensively in the past, and I think it's historically quite interesting, particularly as a contrast to what people do today, and also why people tried to do it long ago. Panic mode is the simplest and most popular method of error recovery that's widely used. And the basic idea is that when an error is detected, the parser is going to begin discarding tokens until one that has a clear role in the language is found. And then it's going to try to restart itself and continue from that point on. And these tokens, the ones that it's looking for, are called the synchronizing tokens. And these are just tokens that have a well-known role in the language, and so that we can reliably identify where we are. So a typical strategy might be to try to skip to the end of a statement or to the end of a function if an error is found in the statement or function, and then begin parsing either the next statement or the next function. So let's look at a simple hypothetical example of panic mode error recovery. So here's an expression. Clearly it has a problem. We shouldn't have two plus signs in a row, so something's gone wrong here at the second plus. And what's going to happen is the parser is going to come along. The parser is going to be proceeding from left to right. It's going to see the open paren. It's going to see the number 1. It's going to see the plus. Everything is good. And then it's going to see this second plus, and it's not going to know what to do. It's going to realize that it's stuck and that there's no expression in the language that has two plus signs in a row, and it needs to do something to recover. It's encountered a parsing error, and it has to take some error action at this point. So in panic mode recovery, what it's going to do is it's going to hit the panic button. So right at this point, it's going to say, I give up, I'm not parsing normally anymore. It goes into a different mode where it is simply throwing away input until it finds something that it recognizes. And for example, we could say that the policy in for this particular kind of error is to skip ahead to the next integer and then try to continue. So it would just throw away the plus in this case, and then it would restart here at the 2, expecting to see another integer, trying to finish off this expression, and it would treat that as 1 plus 2, and then the parentheses would match, and the rest of the expression would parse just fine. Now, in tools such as Bison, which is a widely used parser generator and one that you may use for the project, there's a special terminal symbol called error to describe how much input to skip. And the productions that are given in Bison look like this. So you would say that the possibilities for E are that E could be an integer, E could be the sum of two E's, two expressions. It could be a parenthesized expression, or if none of these work, okay, so these are the normal productions, right? If none of those work, then we could try some of these productions that have error in them. And error is the special symbol for Bison. And it says, well, these are the alternatives to try if these things over here didn't work. So if you find an error, let's focus on this one right here. So what this says is that if you find an error while you're trying to parse an E, okay, and we haven't actually said how that works yet. We'll see that in future videos. But conceptually, the parser is trying to recognize one of these kinds of expressions here. It's in a state where it thinks it wants to see an integer or a plus or a parenthesized expression. And if that isn't working out, if it gets stuck, well, then it can hit the panic button. It can declare that it's in an error state, and it can throw away all the input. This error will match all the input up to the next integer. And then this whole thing could be counted as an E, as one of these things, and then we would try to continue the parsing. Similarly, if we encounter an error somewhere inside a pair of matched parentheses, well, we could just throw away the whole thing and just reset at the parentheses boundaries and then continue parsing. So these are two possible error recovery strategies if we find an error for this particular kind of symbol in the grammar. And you can have these these productions that involve the error token for as many different kinds of symbols in the language as you like. Another common strategy is to use what are known as error productions. And these specify known common mistakes that programmers make, just as alternative productions in the grammar. So here's a simple example. Let's say we were working on a programming language or a compiler for a programming language that was used by a lot of mathematicians. And instead of writing 5 times x, like computer scientists do, these guys always wanted to write 5 blank x, to just juxtapose the 5 and the x to look more like normal mathematical notation. And they complain that this is always giving them parse errors, that the parser is just complaining over and over again that this is not a well-formed expression. Well, we could just go into our grammar and add a production that made it well-formed. We could just say, well, now it's legal if I have that one kind of expression is just to have 2 expressions that are juxtaposed next to each other with no intervening operator. And this has the disadvantage, obviously, of complicating the grammar. If we do this a lot, our grammar is going to get a lot harder to understand. It's going to be a lot harder to maintain. And essentially all this is doing is promoting common mistakes to alternative syntax. But this is used in practice. People do this sort of thing, and you will see, for example, when you use GCC and other production C compilers, they will often warn you about things you're not supposed to do, but they'll accept them anyway. And this is essentially the mechanism by which they do that. The last strategy I want to talk about a little bit is error correction. So far we've just talked about strategies for detecting errors, but we could also try to fix errors. That is, if the program has mistakes in it, the compiler could try to help the programmer out and say, oh, you obviously didn't mean to write that. Let me try to find a program for you that works. And these kind of corrections, in some sense, we want to find programs that are nearby, programs that aren't too different from the programs that the programmer supplied, but we couldn't compile correctly. And there's a few different things that you can do. 2 of the things that people have tried are things like token insertions and deletions. So here you would like to minimize the edit distance. That would be the metric that you would use to determine whether a program was close to the original program that the programmer supplied. You could also do exhaustive search within some bounds to try all possible programs that are close to the program that was supplied. And there are a couple of disadvantages to this, actually a number of disadvantages. You can imagine that this is hard to implement. It's actually quite complex. This will slow down the parsing of correct programs because we need to keep enough state around that we can manage the search or the editing in the case that we actually do encounter an error. And of course, nearby is not really, it's not really all that clear what that means, and various notions of nearby may or may not actually take us to a program that the programmer would actually be happy with. The best known example of error correction is the compiler PLC. This is a PL1 compiler, that's the PL part, and the C stands for either correction or Cornell, which is where the compiler was built. And PLC is well known for being willing to compile absolutely anything. You could give it the phone book. You can, and people did, give it things like the speech from Hamlet's soliloquy, and it would print out a lot of error messages. Sometimes these error messages would be very funny to read, and it would, in the end, do correction and produce always a valid running PL1 program. And you might ask, why do people bother with that? That doesn't seem, but that may not seem very compelling to us today. And you have to realize that when this work was done back in the 1970s, people lived in a very different world. There was a very slow recompilation cycle. It could take a whole day to get your program to compile and run. You would essentially submit your program in the morning, and you might not get results back until the afternoon. And with that kind of turnaround cycle, even one syntax error in your program was devastating. You could lose a whole day because you mistyped a keyword. And having the compiler try to take a stab at finding a working program for you, if the correction was small and you saved an entire day, if it could fix that one small mistake you made and give you a valid run, that was actually a useful thing to do. And so the goal then was to find as many errors in one cycle as possible. They would try to find as many errors, they try to recover, find as many errors as possible, give you as good feedback as possible so you could fix as many errors, avoid as many retry cycles as possible, and even possibly automatically correct the program so that you could see if the corrections were right, and then possibly the results you got back were useful and enabled you to do even more debugging before the next round. Now, today, we're in a completely different situation. We have a very fast, almost interactive recompilation cycle for many projects. And as a result, users generally aren't interested in finding many errors. They tend to correct only one error per cycle. Compilers still report many errors. They'll give you lots and lots of errors. But my observation, certainly my habit personally, and what I see many other people do, is to only fix the first one because it's the most reliable and the one that definitely needs to be fixed before you can try to compile again. If the compilation is fast enough, that's probably the most productive thing to do. And as a result, complex error recovery today is just less compelling than it was a few decades ago.